Yeah.
Okay, can't see the screen. Oh, the smartboard file maybe? This one?
Oh. Okay.
Okay, so for the first part, kids, I just want to let you know that your ISP projects are going to be coming up. Let me just pull oh, there we go. So your ISP projects is going to be, you get to pick your own topic. And explore calculus connections. So if you know you're going to biology or engineering, something like that, you can explore the calculus connections related to whatever your topic is. And you're going to get like 2 or 3 units for that. That will be really vital for your second university deadline. Super important for your second university deadline. So we want you to start researching now. Like, for example, if you're going to business or life sciences, there are textbooks that say calculus in life science, calculus in biology, calculus for engineering. And you're going to be able to use that research into your ISP projects. So please, please, please start that research now. You can find some examples. The reason I've put the Mary Ward STEAM Instagram, we've posted grade 12 work from other previous years, and you can check that out on the Mary Ward STEAM Instagram. So that's why we're starting off with that. Okay, so resultant force. We know from last time that whenever you're adding 2 or more vectors or forces, we call that the resultant vector. For this seminar, it's on the resultant. Turn off some lights. So when 2 vectors act on an object, you can use vector addition, the Pythagorean theorem, and trigonometry to find the resultant. We have shown that if we take any 2 forces that act at the same point, acting at an angle of theta to each other, the forces may be composed to obtain the resultant of these 2 forces. So if you can copy example number 1 into your notes. A sailboat's destination is 8 kilometers east and 6 kilometers north. Find the magnitude and direction in bearing notation of the resultant. So I have a vector here that is heading 8 kilometers east and then 6 kilometers north. So today we're going to explore through aviation problems, tension problems, what a resultant force is.
Please, with Nati Omega, please report to Ms. Sanderson in religion now. Nati Omega, report to Ms. Sanderson in religion now.
So what a resultant force is and how you can calculate it. And we're just going to remind you that this red vector over here represents the sum of 2 forces when the original vectors are lined up tip to tail. So we can easily see the question is asking us to solve for the magnitude and direction. Because we have a right-angled triangle here, we can use the Pythagorean theorem to solve for the magnitude. So I'm just going to, are we on pointer mode? So I'm going to reveal that. There we go. So I'm plugging it into the Pythagorean theorem. R squared is equal to 8 squared plus 6 squared. In order to go from R squared to R, I have to take the square root of the sum And that's how I get the magnitude of my resultant, which is 10 kilometers. But now we have to look for the direction. It's not enough to just solve for the magnitude. And remember, direction can be illustrated in different ways. We can have the quadrant bearing, the true bearing. And from the last seminar, I want you to remind yourself that the true bearing is always calculated from the north line. And we are figuring out what is the angle to the vector when we're going clockwise. So what I have drawn here is the north line, and we're trying to find this angle from the north line to the vector. So I can use my highlighting tool. Here's my highlighter. You can see that this vector, 6 kilometers, and my imaginary north line, those vectors are parallel. And we know the rule, according to parallel lines, our rule is we can draw that Z pattern. We learned that in grade 9. According to that Z pattern, my alternate angles are equal. Okay, so that's going to come up a lot in the different problems. The alternate angles are equal when you have two parallel lines. For some of the questions, we draw in our parallel lines so we can figure out what the alternate angles are. And from that, now I know that this angle is going to be equal to this angle theta within the triangle. So what I'm going to do is now label the triangle, or according to my SOHCAHTOA. So some of you might still remember, because this is the angle that I'm trying to solve for. What is the side that is connected to my angled called? Yeah, adjacent, very good. And the side that is opposite to the angle that I'm trying to solve for is opposite. So can someone tell me what is the only trig ratio that involves opposite and adjacent? Yep, 10. Yes, very good. So if I go to my arrow, in order to solve for the direction, I'm going to say that tan theta is equal to the opposite over the adjacent. So that means that angle theta, and please don't just write theta by itself. Remember, when you're solving for an angle, because we are solving for direction.
Derosian contact 6001, please.
Angle theta is equal to the tan inverse of 8 over 6. So angle theta is equal to 53.1 degrees. Now, we're not going to nitpick about this, but in university, you will find out that whenever you have to state your direction as a true bearing, I'm going to turn this off a little bit. When you have to state your direction as a true bearing, you have to state 3 digits. So that's why the sentence says the resultant displacement is 10 kilometers at a true bearing of 0, 53.1 degrees. And if you are noticing that there's a 0 in front of the degrees in your textbook example, that's just because that's how we state a true bearing direction. Okay, so I'm going to turn it over to Mr. Bullock for the next part, which is the resultant velocity when we talk about aviation.
Okay, so we've already kind of covered what the resultant is and how, sort of how to calculate it, but now we're going to look at some specific application type problems that we can use, and a very common one, and where you see this a lot in the textbook problems and it's used in the real world, is with aviation. So let's just revisit this part one more time. So just a reminder, the resultant velocity of any two velocities is just their sum. And you guys were taught sort of two ways to calculate the sum of any two vectors, okay? You could either draw a parallelogram, or you could draw a parallelogram if the vectors were connected tip to tip, but if they're tip to tail, we could construct a triangle. And that's going to be the primary strategy we use for these types of questions, okay? So we're going to draw a triangle showing the velocities, so there's a clear recognition of the resultant and its relationship to the other two velocities. So we connect them. We draw our third side, which is our resultant. And that's what we're going to be solving for in the majority of these problems. But just some terminology. So for velocity questions involving airplanes or aviation, right? There's a couple things we have to know. The first is that when the velocity of airplanes is mentioned, it's understood that we're referring to what's called its airspeed. Okay, so when you talk about a plane's airspeed, it's always in relation to the air that it's flying in. Okay, when we talk about the velocity of the wind, what we're talking about is its velocity in relation to the ground. So you'll always be given a speed and a direction for that. Okay, the resultant velocity, therefore, of the airplane is when we look at the velocity relative to the ground. And there's an equation we can use for this, and you can note it here. So velocity of the air, you can see that we've labeled it as such, plus that of the wind equals the velocity with respect to the ground. So it's just a formula that we have to kind of understand the language for when we're doing these types of problems. But the way that you set up your vectors and calculations for the resultant are the same. Primary strategy for these ones is drawing triangles as opposed to parallelograms, though. Okay, so what I want you guys actually to try and do for this problem is I just want you to try and draw it as best as you can. And it's okay if you get it wrong, but a lot of these problems just, in order to even start them correctly, doing the math, the operations, we have to work on being able to draw them, to construct them, okay? So this particular problem, we have a plane that's traveling 40 degrees east of north that has this airspeed of 1,000 kilometers per hour. And then we have the plane is traveling at a bearing of 45 degrees east of north at 1,050 kilometers per hour. And it's asking us for the velocity of the wind. So for this one, since they're giving us our bearing direction and speed magnitude, you're going to set up a 4-quadrant system, okay? North, east, south, and west. And I want you to try and draw where those two angles would be. And then since the magnitude, so their speeds for each one are almost similar, right? They're almost exact. They're very similar. Make sure you're scaling it appropriately, right? Like the scale matters for these diagrams. You have to remember that the magnitude, so the length of those vectors, if you're sketching it, it's important to just try your best. Like, because we're going to be using triangle laws anyways to solve it, but you know, don't construct your diagrams with vastly different lengths for your vectors, because here they should be pretty similar. Okay, so I'm going to give you a minute or so. I want you to try to draw this. So I'll kind of put what's my shock here. So what you're going to do is you're going to set up a quadrant system, right? Like this. And you have to decide where this vector, so 40 degrees east of north, what quadrant that would fall in, and then give it a magnitude, a length of 1,000 kilometers per hour, okay? And then I want you to do the same thing for the second one, and then we'll go from there. So it's okay if you get it wrong, just try your best, because it's important to kind of practice just drawing these. Maybe see what the person beside you got, okay? And I'll give you guys a minute to kind of just try and just construct it. And then if you do get it wrong, maybe you can kind of identify where you were either misunderstanding something or having some issues, okay? So I'll just give you a minute. So what does east of north mean again? So remember, you start at your north direction, so that's going up, and then you're rotating east. Okay, so by 40 degrees. Okay, that's how we read that, east of north. Okay, once you think you have both of those vectors, you could connect them. We'll show you in the diagram, but that would be your result for this one. Okay, so I'll just give you a minute. You'll see lots of these types of problems in your textbook. So for the unit work for this one, in the guide as well, okay? Very common application of these types of vector problems.
And just to be clear, your unit 4, we're going to move on to a different concept. So I don't think there's any force and velocity in the unit 4 guide.
Okay, maybe we'll take a look. So you guys came up with, so east of north, so we're starting at our north, I guess we'd call it our north pole, right? Like our vertical upper half of the y-axis, and we're rotating, this case, 40 degrees east and drawing a line that has a magnitude of about 1,000. Now, again, that's going to be different for each of you, but you just need to make sure that both of those vector lines are about the same length because they're almost equal in magnitude. Okay, so let's take a look. Got to zoom out a little bit, I think. So that's what our diagram should look like. Okay. So how do we construct that? We're starting north and we're rotating east 40 degrees for the first vector, and we're drawing a line that's about the same length as our second vector. The second one obviously has to be a little bit longer. Okay. Doesn't be perfect, but just, we'll be looking to kind of see to make sure that at least you understand that, right? And then the second one is we're just rotating 5 degrees past that initial vector line, and it's going to be a little bit longer, and then we can label it as such. Okay. So that's how we construct this one. Now, once you've drawn it, remember what we're looking for again. So let me just draw this line in here. I think I can do this. So what we're looking for is that triangle. We're going to enclose it, right? We're going to connect the ends of those two. And then that's going to be our resultant that we're going to be trying to solve for. The question is, though, what can we use? So let's just label this. This would be, there we go. Okay. Question is, what do we use? I need to solve for that red length line. So when you're deciding what to use, you need to remember trigonometry laws, right? So is this a right angle triangle? Is this a 90-degree triangle? No. So what can't we use? We can't use Pythagorean theorem, and we can't use SOHCAHTOA, right? Sine, cosine, tan. All of those only work with right angle triangles. So we can't use those. In grade 11, you guys learned about how to solve side lengths or angles from non-right angle triangles. And what we use for those ones are either sine law or cosine law. Okay, so for non-right angle triangles, if we're just looking for angles or lengths, that's what we're going to use. Okay, the question is, which one do we use? Do we use sine law or do we use cosine law for this one? So if you're not sure, there's a really easy way to kind of remember which one to use.
I think there is an answer over here.
Oh,
Maybe
do we
you
have an
can
answer? Or
explain why?
do you know why we use cosine law? Yeah.
Very good.
So one of the easy ways to remember which one to use is if the angle that you're given, now remember, we're looking at just this triangle, that 40 degrees is not part of the triangle, that's outside, exterior of the triangle, right? But that 5 degrees is on the inside, and it's comprised of, it's created from the two side lengths, the two legs of the triangle for which we know their magnitudes. So if you are given an angle, an interior angle, that's created from two known side lengths, that's when you can use cosine law. But even that's a little bit complicated, right? Like it's tricky to remember. So like the easiest way to remember which to use out of sine law or cosine law is if you have an angle that you know in the triangle opposite a known side length or magnitude, then that's sine law. If you don't have that, then it's cosine law. It's really that simple. So for example, this, I know the angle, the only angle I know is 5, right? Do I know the length of the side across from it? I don't know that, so I can't use sine law. So I just use cosine law instead. Okay, that's really that simple. You can also remember it that way, which is fine. The angle that you're given is comprised of the two legs of the magnitudes we know. And you could also use cosine law. So for this one, we use cosine law. So just to remind everyone how we use cosine law, the legs of the triangle, so the length of it, we label using lowercase values, lowercase a, b, and c. The angles we label with uppercase values, a, b, and c. And then the angles that are opposite side lengths have the same letters. So for example, if I label 5 degrees, this angle A, uppercase A, the side length across from it would be lowercase a. And then you can use the formula for cosine law, okay? Do I remember it? I think it's a squared equals b squared plus c squared minus 2 times bc times cos A, yes. Okay, that should be in your notes, or that should be in the guide, that should be in the textbook. It's actually in one of the previous lessons we did too. Okay, but all you need to do now is, now I know what those parameters are for this formula. We're just going to plug them in, and we're gonna evaluate this, right? Oh, I didn't use that. So, but the most important part is kind of just knowing which formula to use. Is it on this slide or the next one? Must be on the next one. Oh, there we go. Knowing which one to use, because if you tried using sine law for this example, you would have found you got stuck. Okay, so, and notice the notation we use too. Okay, we're calculating the magnitude of the resultant vector, which in this case is the wind. Okay, so we need to denote it as such, so we use our absolute value notation, vector w, we square it because that's our a squared term for our formula, and then we just plug in the rest of the values into the cosine law. Okay, and just evaluate the right-hand side. So just remember, I wouldn't recommend doing that all in one shot in your calculator, because if you try to do it all in one shot, it's just really easy to kind of mess up one of the, all you need to do is enter one thing in wrong, you get the wrong answer. So you could calculate this separately. We did all in one line here, but you could show 2 or 3 lines of work. You would simplify the squared terms, enter this into your calculator. So how you enter the cos of 5 depends on how your calculator works. Sometimes it would be cos 5 equals, sometimes it's 5 cos equals. So you just need to know how your own calculator works for that. And then evaluate. Okay, and we can round it to the nearest tenth is fine. So it's approximately equal to 102.4 kilometers per hour. Okay, so when you're doing these problems, make sure you're labeling your vector diagram correctly. That takes a lot of practice. Make sure you're choosing the correct trigonometry formula to use based on the information given in the problem. Substitute it in. Try and do your work step by step as opposed to one shot, and then make sure you're using proper notation. Okay, so that's only part of the problem, was to calculate that resultant. All right, remember, for a resultant, not only do we need a magnitude, but we also need a direction. So zoom out a little bit. To state the direction, we're going to keep with the same notation that we used for the original 2 vectors, which was the quadrant bearings, right? So if I just stated the direction as this value of theta, which we haven't calculated yet, that would actually be incorrect because that angle theta is this angle right here, right? But that would not be a quadrant bearing. That is the interior angle of that triangle. If we want to keep the notation the same, the first step is figuring out what that angle is, and then using what we know about opposite angles with transversals back from grade 9 that Miss Albert was talking about, and then using a bit of logic to calculate what the quadrant bearing is going to be. But the first step is to figure out what this angle is, okay, for the direction of our vector. Okay, so we draw a little quadrant system, and here it is here. Okay, so we can draw a north line there because our bearing is going to be with respect to north. And now the question is, how do I determine what that whole angle theta is? Well, the first thing we can recognize is that since the north and the north are parallel here, we could conclude that this particular vector acts as a transversal. You guys remember those in grade 9 where you had 2 parallel lines, you drew a line through them, and then the angles of each had certain properties, right? One of the properties was, and you might remember it called the Z pattern, or I'm not sure, sometimes it's different names, but the fact is those 2 angles are going to be equal. Since the end poles are parallel, if I connect them with a straight line, then those 2 angles are going to be equal. So we can conclude that right away, just from the fact that those north lines are parallel, okay? Which means I really only need to calculate this angle alpha, which we've labeled, and then I can give that a quadrant bearing since it's being rotated about that north line there. So let's first figure out what this angle theta is to start. And the question is, what can we do for that? Well, we're going to use cosine law again. However, remember, there's two versions of cosine law, right? There's the side length version, which we used on the last slide to figure out the magnitude of that resultant. Or if you're searching for an angle, which we are in this case, there's the angle version, okay? Now, at the end of the day, it doesn't matter which one you use. You would still arrive at the same answer. It's just that if you use the incorrect version in terms of its structure, it's just going to take you longer. So like if you use the side length version instead of the angle version, you'll still get the right answer. It's going to take you like 2 to 3 lines more work. So why would you make your life?
And remember, this is just a rearranged version of the other formula that Mr. Bullock wrote on the board, right? We just rearranged it to be solving for the angle versus solving for the side length.
Yeah, exactly. So basically this formula, where did I write? This formula, if you isolate this for cos A, just do some algebra, you'll end up with the angle version, which is right here, okay?
If we were going to test you on this, we always would have given the trig formulas, just in case future years we bring back the test. You would always get the formulas in the test center. In university, they might rely on you memorizing your trig formulas.
Okay. So in this case, we know all 3 side lengths of the triangle, and we're trying to find an angle inside. So we actually could have also used sine law for this one, because I do have this angle 5 across from my resultant, which I calculated on the last slide. So you can choose either one. In this case, we're just using cosine law. You could have used sine law since we have enough information, but we'll just use cosine law. And we're solving for that entire angle theta, which is comprised of the sum of 40 and alpha right now on the last slide. So we enter in the legs of the triangle according to the formula. We enter in on the bottom just the rearranged, and our only goal now is to kind of just evaluate the right hand side. Again, I wouldn't do that in one shot. It might be a little bit much, but what is this sliding, or what is this? Oh,
It should disappear.
oops, what did I do? Oh, there it is. Okay, so we end up getting theta is equal to 116.7 degrees. Okay. Now the thing is, when you were to solve this cos theta equals, remember you'd eventually, since you're solving for an angle, have to do the inverse trig operation with that. So in your calculator, that's the second function cos, and then you would enter in whatever this evaluates to. We're not showing that work for this example,
But
right?
for your unit work, we do
Unit
want
work
you
you
to
should,
break
yeah.
down into steps more.
Okay. And anyway, so what we've calculated is that full angle, right? That full angle, which we drew on the last slide. But I don't want the full angle. I just want alpha here because I want to do my quadrant bearing. So since I know the full angle, I've concluded that this angle on the inside is 40 degrees just by using that transversal. The difference between them would be the angle I'm looking for. Okay. So this is the logic part now. This is kind of the logic part. You've done your trigonometry, you've solved for this angle. We need to find the difference of those two to write our quadrant bearing. Since this alpha angle works out to being 76.7 degrees, well, now I can write my quadrant bearing, but if I wanted to write a quadrant bearing, you could write it in terms of east of north or east of south. Both are okay. But in this case, we've chosen to do it east of south, which means that this angle, if we're rotating from the south pole, not from the north, okay, but from the other direction, from south going east, that's going to be 76.7 degrees east of south instead, okay? So you have to make sure you're comfortable with the quadrant bearing notation. Make sure we covered those in previous lessons. Okay, so just make sure you're good on that. All right, I think that's it for this one, right?
Yeah. I think we're moving on to the equilibrium.
Yeah.
Okay. Might zip along the next section a little bit so we can focus on tension vectors. So it says an equilibrium vector is one that balances another vector or a combination of vectors. It is equal in magnitude, but opposite in direction. And that's the part I really want you to highlight in your notes. Equal in magnitude and opposite in direction. When we apply this to, opposite in direction to the resultant vector. When we apply this in word problems, that is the only part that you really need to comprehend. And we're going to illustrate that in the next word problem. If the equilibriant is added to a given system of vectors, the sum of all vectors, including the equilibriant, is 0. So we have a little example here. And if I line these vectors up from tip to tail and draw the resultant from the tail of the first vector to the tip of the second vector, I have my resultant written in red. Now the equilibriant would balance this resultant so that the sum of the resultant and the equilibriant would be 0, meaning the sum of adding both these vectors up would also be 0. We call that the sum of the system of vectors. And so this equilibriant would be absolutely equal in magnitude, just pointing in the opposite direction. And in order to take vector problems into the real world, we need this whole concept of balancing vectors and having that 0 vector. In the question we're going to be exploring, it's the reason that an object stays stationary. The object doesn't move, even though there are multiple forces acting on the object. And it comes down to this concept of the state of equilibrium. Okay, so Mr. Bullock will do a simple right-angled problem, just like we did in the introduction to the seminar, and then I'm going to give a more complex problem involving the equilibrium that has to deal with tension vectors.
Okay, so let's say we've gone to the circus and we're seeing a clown get shot out of a cannon. All right, so we know the mass of the clown. So the mass of the clown is 80 kilograms. And we know that the force that they're being shot out of is 2,000 newtons, okay? Vertical force is the acceleration due to gravity. That's always a constant. It's always the same. And if you've taken any physics classes, you would know that it's 9.8 meters per second squared, okay? But what we're going to do is find the magnitude and the direction of the resultant force on the clown. So remember, he's being shot horizontally, so straight, relative, parallel to the ground. That's the direction. So we can construct the right-angle triangle for our diagram. So I'm just going to actually just kind of move over a bit. We're going to focus on this part. Okay, so we can start at our initial point. We can draw our vector with a magnitude of 2,000 newtons, okay? And then the force of the downward force, so that is calculated from, and if you take physics courses, we would know this, we're multiplying the mass of the clown by the force of gravity to get our force in newtons. And we know that's acting directly downward because that's how gravity acts, okay? So that's why we go straight to the right for horizontal and straight down for that force acting upon gravity. So basically, we just create a right angle triangle, okay, for our vector diagram. We connect them for our resultant, okay, as we do per normal. And we have a right angle triangle. So now we can use grade 10 sort of methods to kind of do some calculations. Depending on where we're being asked, we can either use Pythagorean theorem or SOHCAHTOA. So this question is asking us to find the magnitude and direction of the resultant force on the clown, okay? So the magnitude we'll find first. So we'll just use Pythagorean theorem for this. So a squared equals b squared plus c squared. Just note how we denote this, right? The magnitude of vector f, we have to write using absolute value notation. And that's not so bad. We just square each, sum them, take the square root, and we end up getting our magnitude of that, 2,148.2. Okay, so that's not so bad. We can even label that over here. So that's 2,148. Oh, there's no, does this work? Oh, nice, okay. what was it, 48? 48.2, okay. Okay, so there's the length, the magnitude of our hypotenuse there. But this question was actually asking us for the resultant, which we've done. So we also need a direction. Okay, so for that, we can just find, since we're gonna, so remember, we've done quadrant bearings, right? But there was also another one we did in terms of direction that is in relation to the horizontal. Makes sense to use that for this question since the clown is being shot horizontally, okay? So this is the angle that we need. And since we have a right angle triangle, we can just use Pythagorean theorem for this one. And you can either use, you can use any of the ratios actually, because I know all of the side lengths of the triangle. So you could use sine, you could use cos, you could use tan, it doesn't matter which one. We just need to remember that this side is the adjacent side, this side is the hypotenuse side, this side is the opposite here. And whichever ratio you choose, you just need to make sure that you're using the corresponding sides according to the formulas. But I think for the example, we ended up using the tangent ratio. Yeah, so we did the opposite over the adjacent. So 784 divided by 2000 is equal to tan theta. And then do calculate that, do your inverse ratio, we end up getting theta is equal to 21.4 degrees. Okay, so remember those resultants, you need a magnitude and a direction. So we can conclude by saying the resultant force has a magnitude of 2,148.2 newtons and a direction of, and the language we could use is 21.4 degrees below. So if you go back to the notes, we've rotated below the horizontal line in order to get that angle. So we have to use that language when we're stating the direction of the resultant, okay? Okay, so that's not bad. The next part of the question, find the magnitude and direction of the equilibrium force on the cloud. Okay, so now, according to what Miss Albert has just told us, that particular vector is going to be equal in magnitude, so it's going to have the same length as our initial resultant, but it's going to be in opposite direction. So the opposite direction means if you were to create an angle from the equilibrium and the resultant, the angle that's created is 180 degrees. So it's going in the complete opposite direction, okay? So we've drawn that in our diagram up here. And so what I was saying was, if you were to draw an angle between those two, that's 180 degrees, okay? So it's in the complete opposite direction, but same magnitude. So now, since it's in the complete opposite direction, if we wanted to state what the direction and magnitude of that is, well, the magnitude we know is the same, right? By definition, the magnitude, the length is the same, but the direction is going to change now, because now I'm not looking for angle theta, now I'm looking for this angle alpha here, okay? But again, what do we know? What did we just learn about those two? The equilibrium and the resultant, they make 180 degrees angle between them. So I could just find the difference between 180 and the angle we solved for, and that will be my angle alpha here. So that's how we show that. We can just say, okay, that's equal to alpha 180 minus theta. So 180 minus 24, and we end up getting 158.6 degrees. And the language we use again, so the magnitude language hasn't changed, but in order for this direction, we can say as a direction of 158.6 degrees counterclockwise, so counterclockwise from the horizontal, okay? So you just have to make sure you're using the correct line for that one.
Okay,
Okay,
perfect.
yeah.
So very last example, I promise, and this is going to be exactly like a question you're expected to do for your unit work. So I'm going to give you a second to copy this down. Let's zoom out. That's enough. Okay, A mass of 20 kilograms is suspended from a ceiling by 2 lengths of rope that make angles of 60 degrees and 45 degrees with the ceiling. Determine the tension in each rope. So instead of writing down the problem, if you can take a second and just copy down the diagram. And this is what we call a position diagram. So when you have these more complex problems, you're going to need 2 diagrams for your solutions, and that's what we're going to be looking for during our consultations. The position diagram shows what is happening based on the question, but nothing is to scale. We're just sketching out information. Remember, we don't know the length of the rope. We don't know the length of the ceiling. We're just sketching out what we do know in the position diagram. Now, what I'm going to do later on is translate the vectors to allow us to calculate, based on the where we align the vectors, the tension in the ropes, because that's what the question, if we go up, it's asking, determine the tension in each of the ropes. That means we are looking for the magnitude of those ropes. So we have this rope that is making a smaller angle with the ceiling, and this rope that's making a larger angle with the ceiling. We also have a mass that is suspended in air with gravity trying to pull it down. So how did I get this, the number of newtons for the force due to gravity? I actually just used my formula. So my force due to gravity is equal to the mass of the object times my gravitational force, which is going to give me 20 times 9.8, which is equal to 196 newtons. Okay, so that's all we need to know from the position diagram. Since the mass is not moving, I know there is tensions in the rope. So even though gravity is pulling down, the tensions in the rope are pulling in the opposite direction. And the tension vectors are keeping the mass stationary because they're pulling against the force due to gravity. And a hint, as if you do 10 or 12 of these, you're going to find that the shorter rope, the one that is making the larger angle with the ceiling, will always have a higher magnitude of tension. That's what you're going to figure out as you do many different examples. And this is one of my favorite problems, and it's just applicable to the real world. Okay, so we have that. I'm not going to get rid of the position diagram. Since the mass is stationary and the object is not falling or moving in midair, this set of vectors are in equilibrium. So what does that mean? That if we add all these vectors up, we are going to get the zero vector. We're going to get an equilibrium vector that is equal in magnitude but pointing in the opposite direction. So now this leads me to my vector diagram. So if I had to just take these tension vectors, get the arrow. If I had to take these tension vectors and replace them, so I'm going to call this vector vector T1 and this vector vector T2. So you can see that. And I'm realigning them from tip to tail, right? I kind of extended the length because I don't know how long those are. That's what I'm trying to solve for, the magnitude. I exaggerated that a little bit, but I just took those vectors and rearranged them into the proper diagram. I don't need those anymore. You can just see now how I got my vector diagram. So I know that my resultant is going to be in equilibrium. That means it's going to be pointing in the opposite direction. And that's why you can see my resultant is moving from the tail of the first vector to the tip of the second vector, but it is equal in magnitude. Okay, so that's where we're going to start off. And I need to solve for all of the the 2 side lengths, the magnitude of T1 and the magnitude of T2, but I actually know a bunch of the angles. So just like Mr. Bullock did before with redrawing an imaginary parallel line north, I'm actually going to draw some horizontal lines in here because the ceiling is making a horizontal line, and I know what angle T1 makes with that horizontal line. I also know what T2 makes with that horizontal line. So on your vector diagram, I want you to go ahead and draw some horizontal lines where T1 and T2 are meeting up. So we're drawing imaginary horizontal lines. I promise you, we're allowed to do this. Okay, I also now want to use my purple to draw what I know. So you can see here T1 with the horizontal line that represents the ceiling. T1 makes a 60-degree angle. So I'm going to draw in a 60-degree angle. And in the same way, with that horizontal line, T2 makes a 45-degree angle, not here, but out here, 45-degree. So based on parallel line theorems and our rule of alternate angles, the Z pattern, whatever you want to call it, if I take these two parallel lines and draw a Z pattern, I can see this 45 degrees matches up with this. Both of those angles are equal. So all of a sudden, I know one, if I think of this as my larger triangle, I know this angle. This angle is going to be 45 degrees plus 60 degrees, which is 105 degrees. So I know an angle in that larger vector diagram. Now I have to figure out some other angles. So we're going to keep going here. Actually, I'll stay on this slide. Now, if I'm just talking about this smaller triangle up here that is divided by this horizontal line, that makes a right angle triangle. Does everyone see that? A right angle triangle? So I know in this right angle triangle, I have 45 degrees, and a 90-degree angle. So a triangle sums up to 180 degrees. If I take 180, subtract 45, subtract 90, I'm also going to get another 45-degree triangle. So I'm on the right track here. Now for this final angle over here, I know that this larger angle, so now I'm talking about the big triangle, the very big triangle. So if I take 180 degrees, and I subtract this larger angle, 105 degrees, and now my smaller triangle, which is 45 degrees, that tells me that this smaller triangle is 30 degrees. So now I have all three angles. I also have a side length because this resultant was 196 newtons. My equilibrium resultant is also 196 newtons. Can anyone tell me, when I know all my angles and one side length, what type of trig formula can I use? Nalawi? The sine law. Excellent, the sine law. So the sine law dictates that the ratio of the magnitude of a side to the sine of its opposite angle is equal for all sines and angles. What that means is, let me illustrate that to you. This formula over here. So, oops, I don't want to move that. Okay, so if you can write this in your notes and see that little triangle, if I can zoom in, I'm going to zoom in a bit. So that's what I was talking about. The side that is opposite to the sine of A is going to be equal to the side B opposite the sine of B, side C opposite sine of C. That's what we're going to use right now. According to our vector diagram, and let me zoom out again. Okay, so according to that vector diagram, all of my side lengths and their opposite angle are going to be equal. So T1, my angle that for T1 is going to be equal to sine of 45, my side length, sorry, for T1 is going to be equal to sine 45 because that's opposite from that side length. And we're trying to solve for the magnitudes here. The side length T2 is going to be opposite to sine 30. And my 196 newtons, I know that side length, that's going to be opposite to sine 105. So in order to solve for T1, I've highlighted T1, I'm going to set that equal to the side where I know the side length as well as the opposite angle. For T2, I've highlighted that same equivalent ratios. These are called equivalent ratios, but I'm going to use T2 over sine 30 and set that equal to the length where I know the length of the resultant over the angle that is opposite from the resultant. That's how I'm going to set this up in order to solve for the magnitudes of my tension vectors. Okay. So when I solve those, that's what this is going to look like. Back to my arrow. So for T1, I set them equal to each other. I simply have to cross multiply and isolate T1. So that tells me I have to multiply 196 times sine 45 and divide that by sine 105. If I punch that into my calculator, don't do it all at once. First, calculate your numerator, 196 times sine 45, press enter, and then divide your denominator. That will give me 143.5 newtons approximately. And I can do the same thing for T2. I'm setting T2 equal, and notice you're always setting it equal to the ratio where you know the magnitude of a particular side length as well as the opposite angle. So I'm cross multiplying 196 times sine 30 and I'm dividing by sine 105, and that gives me approximately 101.5 newtons. And that gives me the magnitude of both side lengths. In previous years, when we would give this vectors test, students would flip through and pray that they had a tension vector question, because these, you'll notice that these questions follow the same method every single time. It's very methodical, it doesn't change. Whereas the aviation questions, because you're dealing with different bearings, angles, directions, there's a lot of diversity and variety and different strategies for those questions. Okay, so your notes, where I know this is a lot to take in, so we have both published our notes, right, Mr. Bullock? And there is one more question with a video projector mass that is hung by a 5-meter rope from the ceiling. This is similar, but I want you to try to attempt this on your own. Again, for this question, you're going to have a position vector as well, a position diagram as well as a vector diagram. As you're moving through Unit 3, you're going to see it's not too long, it's very doable, but please make sure that we're not sending you for a test, so we need to be able to see your solutions, make them very clear, and make sure that you have a position diagram and a vector diagram for most of your problems. And if you're not sure, just come and consult with your teachers and we can clarify whether you need both diagrams. Okay? Okay, everyone, thank you for your patience. Anything else to add, Mr. Bullock?
No.
Okay, wonderful. Okay, have a great day, everyone.